You ever think about the fact that right now there's a robot on Mars with better tech support than your laptop? Like, think about it. Your computer crashes, you call tech support, they put you on hold for 45 minutes, and maybe times they remote in and fix it. Meanwhile, NASA's got a rover sitting 140 million miles away, and when something goes wrong, they just patch it from Earth across the solar system. How is that even possible? Here's what nobody tells you. Fixing a computer in deep space is nothing like fixing your iPhone. When NASA sends a software update to Mars, they're not just clicking install now and hoping for the best. They're playing the highest stakes game of operation you can imagine, where one wrong move doesn't just brick the device, it kills a billion-dollar mission that took a decade to plan. And here's the thing that might shock you. This happens all the time. Not the killing missions part though, that's happened too, but the fixing part. NASA's constantly rewriting code for spacecraft that are already out there, flying through space, doing their jobs. They've saved missions that were basically dead. They've upgraded computers that are older than most people reading this. They've debugged software on a probe that's literally left the solar system. In the next 15 minutes, you're going to understand how engineers solve problems they can't touch on machines they can't see, using communication that takes hours to arrive. And once you see how this works, you'll never look at a software update the same way again. So here's what's really happening when your phone does that thing where it updates overnight and you wake up to new features. That's convenient, right? Apple pushes an update, your phone downloads it, installs it while you sleep, done. Now picture this scenario. You're an engineer at NASA. It's 2013. You're monitoring Voyager 1, a spacecraft that launched in 1977 when Star Wars first came out in theaters. This thing is now 12 billion miles from Earth. That's so far that sunlight takes 17 hours just to reach it. And suddenly, Voyager starts sending back garbage data. Not the sensor's broken garbage, like actual nonsensical ones and zeros that make no sense. The spacecraft's still alive, still talking to you, but it's speaking gibberish. Like if your best friend suddenly started texting you random characters instead of words. You can't drive out there and check it. You can't reboot it remotely and hope that fixes things. You can't even troubleshoot in real time. Every message you send takes 17 hours to get there and another 17 hours to hear back. That's a 34-hour delay between did this fix it and nope, still broken. And this matters because we're not just talking about losing vacation photos here. Voyager 1 is humanity's farthest ambassador. It carries the golden record, a literal message to any aliens who might find it, explaining what humans are. It's the only human-made object in interstellar space. If NASA can't fix this, we lose our only window into what space is like beyond our solar system. But here's the thing nobody talks about. NASA did fix it. They figured out the problem, wrote new code, beamed it 12 billion miles across space, and Voyager started working again. A spacecraft running on computer technology less powerful than a modern car key fob, and they debugged it from Earth. Wild, right? Think about it this way. When you update your phone, you're standing right there. If something goes wrong, you can force restart it. If it's really broken, you take it to the Apple Store. But NASA's dealing with machines they'll never touch again. Once a spacecraft leaves Earth, that's it. Every line of code has to work perfectly or the mission dies. So how do they do it? How do you fix a computer you can't see, can't touch, and can barely talk to? Here's what I call the time prison. Every single thing NASA does in deep space is trapped by the speed of light, and you can't negotiate with physics. Let's say something goes wrong with the Perseverance rover on Mars right now. Mars is currently about 12 light minutes away. That means if Perseverance hits a problem and sends a distress signal, NASA won't hear about it for 12 minutes. Then, once the engineers figure out a fix and send new instructions, those take another 12 minutes to arrive. That's a 24-minute turnaround on the fastest response possible. No real-time troubleshooting. No, try this. Now try this. Every command has to be thought through completely before you send it because you won't know if it worked for half an hour. It's like playing chess against someone where you mail each move and wait days for their response. Except the chess pieces are a $2 billion rover, and if you make the wrong move, the game's over forever. And here's where it gets interesting. NASA can't just send code and cross their fingers, because here's what happens if they mess up. The spacecraft stops listening. Most deep space probes have a fail-safe mode. If something goes catastrophically wrong, like if bad code crashes the main computer, the spacecraft automatically switches to a backup system. This backup is super basic. It just keeps the spacecraft alive and pointed toward Earth. But here's the catch. It might not listen to new commands the same way. It might not have the same capabilities. And if NASA can't talk to it properly, the mission's basically over. This happened with the Mars Global Surveyor in 2006. Engineers sent a routine software update. Something went wrong. The spacecraft's solar panels didn't track the sun correctly. The batteries died. NASA lost contact, and they never got it back. One update, one mistake. Mission over. So NASA developed this pattern I call paranoid perfection. Every single command they send to deep space goes through an absurd amount of checking. We're talking months of testing for a software patch that might take 30 seconds to install. Here's how it actually works. Let's say engineers discover a bug in Perseverance's code. Maybe the rover's getting stuck in a routine that drains battery. They need to fix it. So they write new code. But they don't just write it and send it. They load it into an exact replica of the rover sitting in a clean room at JPL, that's Jet Propulsion Laboratory in California. This replica has the same hardware, same software, same everything. They call it a twin. And they test the new code on the twin for weeks. They run it through every scenario they can imagine. They try to break it deliberately. They simulate Mars conditions, temperature swings, radiation, dust storms. They make sure this code won't just fix the problem, but also won't create 10 new problems. Only after it works perfectly on Earth do they even think about sending it to Mars. But here's what makes this even more surprising. Even after all that testing, they don't just blast the code up there and hit execute. They send it in pieces. They send checksums, basically mathematical proof that the data arrived uncorrupted. They have the rover verify every single bit before doing anything with it. Think of it like downloading a massive file, but you check the MD5 hash before opening it, then you check it again, then you check it 3 more times, then you back up your entire system, then you run it in a sandbox, and only then, after you're absolutely positive, do you actually execute it. Because space is brutal to data. Cosmic rays flip bits randomly, solar flares can corrupt signals, distance makes signals weak and noisy. By the time a message travels from Earth to Mars, it's like playing telephone across 140 million miles of empty space filled with radiation. This is why the Deep Space Network exists. Most people have never heard of it, but it's one of the most important pieces of infrastructure NASA has. The Deep Space Network is basically 3 giant radio dishes. One in California, one in Spain, one in Australia. They're spaced around Earth, so at least one is always facing any given spacecraft. These dishes are massive. The biggest ones are 230 feet across. That's like a 20-story building lying on its side. And all they do is talk to spacecraft. They beam up commands and download data. Every Mars rover, every Jupiter probe, every mission beyond Earth orbit, they all rely on the DSN. Without it, NASA would be completely deaf and mute to everything in deep space. But here's the sneaky part. Even with the DSN, bandwidth is terrible. Perseverance can send data back to Earth at about 2 megabits per second at best. That sounds okay until you realize that's when Mars is close and conditions are perfect. Most of the time, it's way slower. We're talking kilobits per second. Dial-up internet speeds, for comparison, your Netflix stream runs at about 25 megabits per second. So NASA can't just upload a massive new operating system. They have to be surgical, they patch specific modules, they compress everything, they prioritize ruthlessly. Every byte matters when you're working with cosmic dial-up. Now here's what nobody wants to admit. Sometimes the fix itself is terrifying to attempt. Let me tell you about what happened with Opportunity, the Mars rover that was supposed to last 90 days and ended up working for 15 years. In 2015, Opportunity started having memory problems. Flash memory, the same type that's in your phone, was wearing out. Specific memory sectors were failing. The engineers at NASA faced a horrible choice. They could keep using the degraded memory and hope nothing critical failed. Or they could do something radical. Reformat the entire flash memory system while the rover was sitting on Mars. Think about that. You're reformatting the hard drive of a computer that's on another planet millions of miles away with a 24-minute communication delay, knowing that if anything goes wrong during the reformat, the rover becomes a very expensive paperweight. Your laptop warns you not to turn it off during updates. Imagine doing that update knowing you can't turn it back on if it fails. You can't reach it. You can't hard reboot it. You just have to trust that the code is perfect and nothing weird happens during the 20 minutes it takes to execute. NASA did it. They reformatted Opportunity's flash memory from Earth. And it worked. The rover kept going for 3 more years until a dust storm finally killed it in 2018. That's paranoid perfection in action. Test everything 1,000 times, then hold your breath and execute, knowing you only get one shot. Here's what's really going on behind all of this. NASA isn't just fixing bugs. They're fundamentally rewriting what these spacecraft can do years after launch. Take the Voyager probes again. Voyager 1 and 2 launched in 1977 with computers that had 69 kilobytes of memory. That's not a typo. 69 kilobytes. A single iPhone photo today is about 3 megabytes. That's 50 times more data than Voyager's entire computer can hold. But NASA's rewritten Voyager's code dozens of times over the decades. They've completely changed how it operates. They've turned off systems that aren't needed anymore to save power. They've reprioritized which instruments send data. They've even changed how Voyager talks to Earth because the original communication system was designed for when Voyager was near Jupiter, not when it's in interstellar space. This is like taking a 1977 Ford Pinto and through pure software updates, keeping it running perfectly while also making it drive better than it did when it was new. You can't upgrade the hardware. You can't swap in new parts. You just have to be so clever with the code that you squeeze more capability out of ancient electronics. And this connects to something even deeper. These spacecraft are running on hardware that was obsolete before most of us were born. The software has to be written in assembly language or very low-level C code because these computers don't have operating systems like Windows or Mac OS. Every instruction matters. Every byte of memory is precious. Modern software developers can be kind of sloppy because memory and processing power are cheap. Your laptop has 16 gigabytes of RAM and can afford to waste some. But writing code for deep space missions is like writing poetry, where every word has to do triple duty. There's no room for bloat. Let me tell you about 2 different approaches to space computing and how they reveal everything about this challenge. Meet Sarah. Sarah's working on a commercial satellite. It's in low Earth orbit, close enough that communication is basically instant. If something goes wrong, she can troubleshoot in real time. She can send a quick fix, see if it works, tweak it, send another version. The satellite's also designed with redundancy. Multiple processors, multiple systems. If one fails, others take over. Sarah's updating the satellite's navigation code. She writes the patch, runs it through some tests, uploads it during the satellite's next pass overhead. Takes about 20 minutes total. The satellite confirms it worked. Done. She grabs lunch. Now compare that to Marcus. Marcus works on the Europa Clipper mission, a probe heading to Jupiter's moon Europa. It won't arrive until 2030. But Marcus is writing code right now that might need to be updated after launch. Here's what Marcus understands that makes his job completely different. He's writing code for hardware he can't fully test yet, for conditions he can't perfectly predict, knowing that once the probe leaves Earth, every fix takes hours to transmit and days to verify. Marcus spends 6 months on a single software module. He simulates everything. He tests on duplicate hardware. He brings in other engineers to try to break his code. He writes documentation explaining every single choice he made. Because 10 years from now, when something goes wrong, different engineers will need to understand his thinking to write a fix. The difference? Sarah's working in a world where mistakes are fixable quickly. Marcus is working in a world where prevention is everything because fixes are agonizingly slow and risky. Notice how different their timelines are? That's because the physics of space communication changes everything about software development. It's not about being smarter or more skilled. It's about understanding that distance creates an entirely different engineering discipline. Here's what most people don't realize. Fixing computers in deep space isn't actually about computers. It's about embracing radical uncertainty while maintaining absolute precision. Think about how we normally solve technical problems. Something breaks, we try a fix, we see what happens, we adjust. That's how humans learn through rapid iteration and feedback. But in deep space, you don't get that feedback loop. You get one very slow, very expensive attempt. And you have to get it right based on limited information. The engineers who succeed in this world don't have superhuman intelligence. They understand that space missions operate on a completely different set of rules. They've accepted that you can't just try something and see what happens. Every action has to be thought through to its logical conclusion before you take it. It's not about preventing all problems. That's impossible. It's about building systems that can survive problems and can be fixed remotely by people who won't know what went wrong until long after it happened. These patterns aren't unique to space exploration. They're about working in any environment where the cost of failure is huge and the ability to fix things is limited. This is the same framework that applies to deep-sea robotics, to Arctic research stations, to any system where just go fix it isn't an option. So here's what we've uncovered. NASA fixes computers in deep space through this dance between paranoid testing and careful execution. They simulate everything on Earth. They send commands in verified chunks. They build in fail-safes. They accept that communication is slow and plan accordingly. Plus, there's the deep space network making any of this possible. And it all connects to this fundamental insight. Sometimes the hardest part of solving a problem isn't finding the solution, it's implementing it when you can't be there to watch it happen. The question isn't whether NASA can fix spacecraft from millions of miles away. They've done it dozens of times. The question is, what happens when we push even further out? Voyager 1 is now so far away that signals take more than 22 hours each way. Soon, we'll have missions to Neptune, to the Kuiper Belt, to interstellar space where the time delays are measured in days. At some point, spacecraft will have to fix themselves, because waiting for Earth's response will take too long. They'll need AI that can diagnose problems and implement solutions autonomously. NASA's already working on this. Future Mars missions might have rovers that can reprogram themselves based on local conditions, only checking in with Earth when something major happens. The engineers fixing Voyager in 2024 are essentially playing tech support for a computer from 1977 that's in a place no human has ever been. They're writing code for hardware that predates the internet, sending it through space at the speed of light, trusting that decades-old electronics will execute it perfectly. That's not just engineering. That's faith in the power of careful thinking, thorough testing, and understanding that some problems can't be solved quickly, they have to be solved correctly. So next time your phone updates overnight and something weird happens, think about the fact that NASA's doing the same thing with rovers on Mars, except their version of turning it off and on again takes 24 minutes minimum, costs thousands of dollars in antenna time, and if it fails, they might lose $1 billion mission. Because once you see how much thought goes into fixing something unfixable, you start to appreciate every working system a little bit differently. Every software update that goes smoothly represents thousands of hours of testing you never see. Every spacecraft still functioning after decades represents problems solved that most of us never knew existed. And maybe that's the real lesson here. The hardest problems aren't the ones we can't solve. They're the ones we can only solve once, where the cost of being wrong is so high that paranoid perfection isn't overkill, it's survival.